So in this exercise, we are going to have a look at Gibbs free energy and the calculations that we can do surrounding it. Um, for the first question, we have nitrogen reacting with oxygen to form 2 moles of nitrogen monoxide. So we have a list of our equations here, and the one that's most suitable is this one, where it says this free energy is equal to the enthalpy minus the temperature times the change in entropy. So in this example, we have both delta H and delta S. So we're just going to substitute it in. So delta H is 180.7 kilojoules minus 298 times entropy. So entropy, you'll notice, is in joules, not kilojoules, so we're going to convert that. And we get plus 173.3 kilojoules. Significant figures, it's 173 kilojoules. The question asks, is this reaction spontaneous or thermodynamically favored? And the answer is no. This is non-spontaneous because delta G is greater than 0. Next up, we have a question that's very similar. It tells us a reaction. It doesn't tell us what the reaction is, but it does tell us the enthalpy and entropy of the reaction. And first of all, it asks if the reaction is exothermic or endothermic. So we see delta H is below 0. So since delta H is less than 0, it is exothermic. The next question is, does the reaction lead to an increase or decrease in randomness or disorder? Well, delta S is greater than 0, so it leads to an increase. It says calculate delta G at 298. So delta G is equal to delta H minus T delta S. Delta G is equal to delta G is equal to negative 19.5 kilojoules. And we subtract the temperature times the entropy. And we get delta G is equal to negative 32.2 kilojoules. So finally, the question is asking us, is this reaction spontaneous? Is this reaction going to proceed from left to right or in the forward direction? And since delta G is less than 0, yes, this is thermodynamically favored. So the next page of questions has us doing a little bit of comparisons. So for each question, we're being asked to calculate delta H, delta S, and delta G using Hess's law, and then we're going to compare it to the delta G we calculate using the summary equation. So first, let's solve for enthalpy. So the enthalpy of reaction is equal to 2 times the enthalpy of HF minus 1 mole times the enthalpy of F2 minus 1 times the enthalpy of H2. Delta H of reaction is equal to 2 times negative 268.61 kilojoules minus 1 times 0 minus 1 times 0. We're just getting these numbers from Appendix C, or a table of thermodynamic values, just paying attention to our states. Delta H of reaction is equal to negative 587.22 kilojoules. Now we move to delta S of reaction is equal to 2SHF minus 1S of F2 minus 1S of H2. So we're doing exactly the same thing. we know that during enthalpy calculations that pure substances like hydrogen and fluorine gas are zeros. That is not true for entropy, so we actually have a little bit more work to do here. So delta S of reaction is equal to 2 times 173.51 minus 130.58 minus 202.7, and that's equal to 13.74 joules per Kelvin. We do the exact same thing again for the third value, which is delta G, and these are all standards. We end up with 2 delta G HF minus 1 delta G F2 minus 1 delta G H2. And when we do that calculation, we end up with negative 541.40 kilojoules per mole. Actually, just kilojoules. So now we're asked to show the exact same thing using the other calculations. So we're going to say delta G is equal to delta H minus T delta S. And that's equal to negative 587.22 minus 298K times 0.01374. Delta G is equal to negative 541.31 kilojoules. So that's very, very close to what we would have had. And we would proceed for each of these calculations, each of these problems exactly the same. I don't really think it is worth the time to go through each of these calculations. It's great practice to actually go through and use Hess's law. But for this one, we have delta H, delta S, and delta G. So when you use Hess's law to calculate them, you'll find delta H is 106.7, delta S is negative 142.2 joules per Kelvin, and delta G is negative 64.3 kilojoules. And when you do your calculation, delta G equals negative 106.7 kilojoules minus 298 times 0.1422 negative. Delta G is equal to negative 64.3 kilojoules, which is again very similar to what we've done already. Again, used in black, we use the Hess's law, the products minus the reactants, all multiplied by their coefficients. And down here, we're just using the values that we've described in black to solve delta G the second way. So if you solve delta H and delta S, you could use what's in orange to find delta G and be fairly accurate. For part C, delta H, delta S, and delta G. And when you apply Hess's law using appendix C, you get delta H is negative 508.3 kilojoules, delta S is negative 178 joules per Kelvin, and delta G is negative 465.8 kilojoules. So again, that's Hess's law. When you solve it with delta G equals negative 508.3 minus 298 times 0.178 joule per Kelvin, delta G is equal to negative 455.1 kilojoules, which is a little bit different, but pretty close. So it says a certain reaction is spontaneous or non-spontaneous at minus 25 degrees Celsius. So right off the bat, I know I'm going to deal with an absolute scale. I'm going to write 248 Kelvin for that. So a certain reaction is non-spontaneous at minus 25 C. The entropy change of the reaction is 95 joules per Kelvin. What can you conclude about the sign and magnitude of delta H? So we know that delta G has to be greater than 0 because it is non-spontaneous. So if we do the entropy term calculation, we know that the uh, the entropy term will be equal to negative 248 times 0.095 kilojoules. And when we do this calculation, 248, 0.095, we know that we're going to have negative 23.56 kilojoules on the entropy term. In order for this reaction to be non-spontaneous, we know that delta H must be greater than negative 23.56 kilojoules. So our conclusion is just that in order for this expression to be true, we need to make G bigger. If this term here is negative 23.56, including the negative sign, then this would have had to be bigger than that. So that's how we would figure that particular question out. So for a particular reaction, delta H is minus 32 kilojoules and delta S is minus 98. At what temperature will delta G equal 0? So delta G is equal to delta H minus T delta S. So 0 equals delta H minus T delta S. T delta S is equal to delta H. T is equal to delta H over delta S. So we just come and rearrange that equation, solving for T, set G to 0. So T is equal to negative 32,000 joules divided by 98 joules per Kelvin, and we get 326 Kelvin. So for part B, we would really defer to the chart. If T is increased from that with part A, the reaction becomes more spontaneous or more non-spontaneous. So with a negative enthalpy term and a negative entropy term, as we increase the temperature, the reaction will become more non-spontaneous. So just to confirm that, delta G is equal to delta H minus T delta S. So delta G is equal to negative 32 kilojoules minus T times negative 0.098 kilojoules per Kelvin. So the negative sign in here turns this positive because we have two negatives, they cancel. So as T gets bigger, this term is going to basically undo this negative effect of the enthalpy. So as T increases, delta G will get closer to 0 and eventually become positive. Reactions in which a substance is composed by losing CO are called decarbonylation reactions. The decarbonylation of acetic acid proceeds as follows. So we have acetic acid going to methanol and carbon monoxide. By using the values in Appendix C, calculate the minimum temperature by which this process will be spontaneous under normal conditions. So we're going to solve for delta H is equal to 1 mole times the delta H for CO gas plus 1 mole times the delta H of CH3OH minus 1 mole times the delta H of CH3COOH delta H standard will equal 175.3 kilojoules when you go through and do those calculations. We'll also do the same calculations for delta S. And again, we fill the values in from the chart for those entropies, and we end up with the standard entropy change equal to 275.7 joule per Kelvin. This makes sense. It's a pretty big increase, but we're going from 1 mole of liquids to 2 moles of gas, so the increase is quite large. Temperature is equal to delta H over delta S. So we used this earlier, and when we did this earlier, we just set delta G equal to 0 and arrived at this particular expression. So 175.3 or 0.275.7. I don't need the point there. This equals 636 Kelvin. This reaction will then become non-spontaneous. Sorry, become spontaneous. So the final part of this assignment is 2 theory-based questions. Number 7 says the reaction of magnesium with oxygen produces magnesium oxide. If you've seen this reaction, it's essentially just the combustion of magnesium. And it's usually very exothermic. So we've stated in our course that the entropy of the system plus the entropy of the surroundings is equal to the entropy of the universe. And we also stated that for any spontaneous process, delta S of the universe must be greater than 0. So the entropy of the universe must increase for any spontaneous process. That's all it says. So since we're going from 3 moles to 2 moles, in definitely a gas going to a solid, we know that we're going to have a decrease in entropy in this reaction, but this reaction is quite favored. In the presence of oxygen, magnesium will ignite. Normally how that works is that usually when the reaction does go, it is extremely exothermic, and that's kind of how we balance this. The delta H is incredibly negative. So the answer for this is no, it doesn't break the second law, because the change in entropy of the surroundings could be more positive than the delta H of the system is negative. So it doesn't have to break the law. So ammonium nitrate dissolves spontaneously and endothermically in water at room temperature. What can you deduce about the sign of the entropy for this process? So first of all, we have ammonium nitrate, NH4, NO3, solid, dissociating into those 2 aqueous compounds. So we have 1 mole going to 2 moles. We have a solid going to aqueous. So we know that the change in entropy for this is very likely greater than 0. You can even go out on a limb and say that it is greater than 0. There are 2 things that really are going to govern this. We know that this is going to be greater than 0. So we know that delta G is greater than 0, meaning that delta G is less than 0, meaning that this reaction is very spontaneous. So we know that delta G is equal to delta H minus T delta S. So when we look at this particular equation, what we know is that, so we set this to 0, delta H is equal to T delta S. So no matter what we do, if this is positive, then this must also be positive just to make that true, because otherwise you would have a negative sign and they would not be equal. So in this particular setting, if delta H is positive, then delta S needs to be, assuming it is thermodynamically favored, and that would count as a proof here.